So we are still working on relative extrema, and I'm going to show you one more example of this, except for it's going to be in a different format than what we have seen so far. So this one asks us to do the same thing that we did in the last example. Find the critical values and classify them as a relative max, relative min, or neither. Also find the intervals of increase and decrease. So that's nothing new. The thing that is new is that this is a derivative. So it gives us the derivative of the function. It gives us h prime of x. And so you might be at a loss of what to do with this since it gives us the derivative of the function rather than the original of the function. But I'm telling you not to fear because this actually decreases the amount of work because it does the majority of the work for you. In step number 2, it asked you to find the derivative. Well, we don't have to find the derivative if the derivative is already computed for us. So that actually takes out the calculus part of this here for you. You don't have to compute the derivative when it's given. Okay, so let's do the rest of the steps. Number 1, finding the domain. Remember, domain asks for when our denominator is equal to 0 or when we take square roots of negative numbers. In this one, we have the denominator x squared plus 3 quantity squared. So we need to know when it's equal to 0. And we don't have any square roots in this function, so we don't have to worry about that. If I square root both sides, and that eliminates the square here. And of course, on the right-hand side, square root of 0 is just 0. So then if I move my 3 over to the opposite side, that gives me x squared is equal to negative 3. Square root both sides again. Don't forget to force in a plus or minus. So we get x is equal to positive or negative square root of 3i. But since we have an I here that's an imaginary number, well, that doesn't make any sense. So I can't have imaginary numbers excluded from the domain. So that means then my domain is all real numbers, as far as we know it. Now, the original function might have a little bit different domain than the derivative, but for the most part, they mimic each other. So if this is going to be in the denominator of the derivative, this is also going to be in the denominator of the original function. So nothing's excluded, so my domain is all real numbers. Step number 2 is to compute the derivative, which is already done for us. So we get to move on to step number 3, which is to set our derivative 2x minus 1 squared times x plus 7 cubed over x squared plus 3 squared equal to 0. We know we get to eliminate the denominator by using our magic trick. We know we basically can ignore our powers for the same reason that we got to ignore the square over here. So this tells me that I have a critical value if I set this equal to 0, or when x is equal to 1/2, or when I set this equal to 0, or when x is equal to negative 7. Now, I skipped quite a few steps there, so if you need to show all that work for yourself, no big deal. Go ahead and pause the video and take the time to do that for you. Okay, now I need to plug those numbers on a number line. So I have negative 7 and 1/2, and I need to test points in between those numbers to plug them in to see whether I have positive or negative. Well, another wonderful thing about this being done for us is that it's already in factored form for us. So let's test something less than negative 7, like negative 8. So if I get a negative 8, and if I plug it into my first piece, it doesn't matter what it is because I have something squared. Something squared will always be positive. If I take negative 8 and plug it into this piece, negative 8 plus 7 gives me a negative 1. Negative 1, an odd amount of times, ends up to be negative. And my denominator, again, I have something squared, so that means this will always be positive as well. Positive times negative divided by positive will end up to be negative. So this is negative, and this is decreasing. Now I need to test something in between negative 7 and 1/2. So the easiest thing is to plug in 0. Remember, I really don't have to test either the first or the bottom because those are squared, and anytime we have an even exponent, it's guaranteed to come up to be positive. So all we have to do is test this piece over here. If I take 0 plus 7, that gives me 7. And if I take it an odd amount of times, like 3 times, that ends up to be positive. So this gives me positive, which tells me that my graph is increasing from negative 7 to 1/2. Last, I need to test something beyond 1/2. I'm just going to randomly pick 5, but anything larger than 1/2 is fine. I don't have to test the first or the bottom, so I just need to test this interval here. 5 plus 7 is positive. Positive an odd amount of times is positive. So this is positive, so this is increasing there. So that was step number 5. So step number 6 then is to select my answer. So in this answer, I'm trying to do all of these things here. I'm trying to figure out where I'm increasing and decreasing. So I'm increasing from negative 7 to 1/2 and from 1/2 to infinity. I always prefer to separate out my intervals because at 1/2 I know it stops increasing momentarily. And then I know it's decreasing from negative infinity to negative 7. So that's half of my answer. The other half of my answer is to find the critical values and classify them. Are they a max, or are they a min, or are they neither? So I have a critical value at negative 7. And that is a low point on my graph because it goes from down to up. So that one is a minimum. I have a critical value at 1/2. That one is neither a low point nor a high point on the graph because it doesn't switch between increasing and decreasing. So x equals 1/2 is a neither. Now what that's actually doing on the graph is that's a plateau on the graph. It flattens out for a bit and then it goes back the same direction that it's coming from. So we've worked through this example of classifying all critical values and then also specifying whether my graph is increasing or decreasing. Now the disadvantage of this one coming as the derivative is that we cannot check this with the graphing calculator. To check this with the graphing calculator, we would need to plug in the original function, and we don't have that, so we're not allowed to do that part here. But I'm pretty confident that we have the right answer, so I think that we can end this example here.